and welcome back to another episode of the natural number game using Lean 4. Today we'll be working on the advanced proposition world. Let's start with level 1, the split tactic. So we have our example where P and Q propositions. We have an instance P of type P, instance lowercase q of type Q, and we have P and Q. To prove that's true. And then this symbol here is the logical AND. If P and Q are propositions, then P and Q is the proposition P and Q. If your goal is P and Q, then you make progress with the split tactic, namely turning one goal P and Q into P and Q. Into a goal of P and a goal of Q. So let's figure out how to do this. So the the tactic would be split in Lean 3, but for Lean 4, we have a different tactic that we're going to use, something called constructor. So split is used for breaking nested if-then and match expressions. Constructor, and you see the split tactic had failed, but the constructor tactic, that's for matching on an inductive type, and it seems like AND is an inductive type with two different cases. And now after the constructor tactic, we have this case left, which is just P, case right, which is just Q. And so we could do exact P, because we have an instance of P, and exact Q to solve both of them. Nice. And that's our level 1 done with the constructor tactic to split a logical AND into the left and right case. Nice. And then here we're going to try to prove something else, that AND is symmetrical. So lemma and sim PQ propositions. And then we want to prove that if P and Q implies Q and P. And how we're going to do that, so before we had P and Q as our goal, but now we have P and Q as in the hypothesis. So let's intro our intro our hypothesis H. Lemma. So we need to. This is lemma. We want to import and open MyNat. Cool. So we have H, which is P or Q, or P and Q, and then we want to prove Q and P. So let's see how we can do this. Okay, here the cases tactic lets us make progress on this. So in cases on H with what? So this is kind of similar to the induction tactic. Splits the main goal, producing one goal for each constructor of the inductive type, in which the target is replaced by a general instance of that constructor. So in our case, it seems like we only have one case for the AND inductive type, where we just have both P and Q. So we can, in this case it's called intro, so we'll call it intro PQ. Sorry, in this case we have PQ and we want to prove P and Q, and we can just do something similar to what we did before. is we'll call constructor, and then exact Q, exact P, oops, and then takes care of and symmetrical using the cases tactic. And transitive, okay. So let's move on to next example, lemma and transitive. Prove the transitivity of the AND logic operator, PQR all propositions, P and Q implies Q and R, or and P and R. Did I do that right? Let's see. P and Q implies Q, implies Q and P, or Q and R, which implies P and R. Okay, if P and Q and R are true falsy expressions, then P and Q and Q and R imply P and R. Nice, so we can, I guess, intro our cases. Intro H1, H2. Okay. And then let's think how to do this. Do we just do cases twice? So cases H1 with intro PQ. Intro of cases H2 with intro QR. Constructor exact P, exact R. Okay, so in our first case, we kind of just like did and like the logic we did for and symmetrical twice is we took our H1 and our H2, we introed P and Q from H1, Q and R from H2, and then we showed P and we showed Q, R. And that's and transitive. Moving on, we have if and only if transitive. Lemma if and only if transitive. So we want to show that the mathematical statement P if and only Q is equivalent to P implies Q and Q implies P. Let's figure out how to do that. So we have P, Q, R, all propositions. And we want to have P, P if and only if Q implies Q if and only if, R implies P if and only if R. Okay. Let's actually make this a little bigger. I realized I was really zoomed in for this. Or really not zoomed in for this. That looks a little better. Okay, so let's look at this. Intro will have, I guess I call it PQ, QR. Okay. And then cases QP with, what do we have for QP? Intro with names intro. What do we have? Do we just have Q and P again? Okay, so for when we have intro, we have let's call this, I don't know, H1, H2, H1. This is not a good name, so this is PQ and this is QP. Okay, so the cases for our if and only if is we just split into implication both ways. So P implies Q and Q implies P. You can see that here. And how do we show P implies R? I guess we can use and transitive twice. Cases H2 with intro, probably QR RQ. Is that what these are called? Yeah, QR RQ. And constructor. Constructor should split us into two cases. Maybe. Unsolved goals. Yes, P implies R and R implies P. And then we could do that with exact and transitive. So the first case is we want P implies R. So exact and transitive of what P implies R. So we want PQ QR. Did that work? Why are you unhappy? P implies Q, Q implies R. Or I guess, we want to prove, what do we want to prove? We want to prove P implies R here. And transitive takes P and Q, Q and R. This is not P and Q. This is P implies Q. Not quite what we want. We want to get P implies R. I guess we can, how do we deal with a P implies R? Constructor, how do we deal with an implication? Let me think. All right, this is just what we were doing in the proposition world where we intro things and then we apply things. So here we can, since our case is P implies R, so we can intro P and then we can exact P QR of PQ of P. And that solves our first case. Right? Because this should be R. Yes. And now we have our case. We can intro R. We can exact to get R, to get P from R, we get Q from R, QR from R, and then we call QP on that. And that should solve, let's see, QR. Oh, RQ, we use RQ. And that solves if and only if transitive. Nice. Let's move on. Let's actually stop right here. That's some nice progress on the advanced proposition world. We're able to learn about the and propositions with ands, split it with constructor, and if that was in our goal, and then if it was in our hypothesis, use cases on it to split it up there. And there I'll prove a few interesting lemmas that and is symmetric, and is transitive, and if and only if is transitive. Next time we'll be doing more. Next episode we'll be doing more stuff with advanced propositions and learning about how to deal with or, and proving cool things about and or. Talking about we'll also talk about proof by contradictions and the law of excluded middle. Thanks so much for watching.